You were taught to laugh at Uranus long before you were taught to understand it. The name shows up. The classroom snickers. The teacher moves on and the planet gets filed under joke in your head. But look at the basic facts. Uranus is about 4 times Earth's diameter, around 51,000 kilometers, about 32,000 miles across, and about 14.5 times Earth's mass. Mars, the famous planet, is less than half that width. So why does the huge one feel like background noise, while the smaller one feels like the main character? That gap is not there because Uranus is boring, it is there because your attention was pushed away. The joke trains you to switch off serious thinking as soon as you hear the name. You don't ask simple questions: what is the weather like there? How strong are the winds? What kind of moons orbit it? Why do scientists keep saying ice giants are crucial for understanding other solar systems? You just accept a vague picture. Big blue far away, probably dull. The first misunderstanding is psychological, not scientific. You were never encouraged to care. Then another layer lands on top, the boring blue ball picture. When most people picture Uranus, they see a smooth, pale blue-green disk. No bands like Jupiter, no obvious storms like Saturn, just a flat sphere. That image comes from one visitor, Voyager 2, which flew past Uranus in 1986. It did not stop or go into orbit. It shot through the system at about 15 kilometers per second, roughly 33,000 miles per hour, dozens of times faster than a rifle bullet. For a few days it was close enough to gather images and measurements, and then it was on its way to Neptune. Even in that short time, the geometry was stacked against you. When Voyager 2 arrived, Uranus's south pole was pointed almost straight at the sun. Instead of seeing the planet lit from the side with a clear day-night boundary and shadows, you got a pole pointed at the light source, everything in similar brightness. The cameras were excellent for the 1980s, but nowhere near as sensitive as the instruments we have today. Under those conditions, the visible light photo showed a disk that looked nearly featureless, so the public saw that cyan, clean, totally smooth disk and concluded the planet itself must be that simple. No stripes, no dramatic spot, no obvious chaos, so your brain files it under calm. In reality, atmospheric motion was still happening, but the combination of viewing angle, lighting, camera limits, and the specific wavelengths used hid most of that structure. One set of images, taken under one setup, turned into the default portrait for decades. Now, add the timescale. Uranus takes about 84 Earth years to go once around the Sun. Its seasons are not 3 months each. They last roughly 21 years per phase. Voyager 2 caught Uranus at one extreme, a configuration where one pole was in long-term sunlight and the opposite hemisphere was in deep darkness. That single seasonal state quietly turned into normal in a lot of people's minds. You were not reminded that this was one frame from an 84-year-long cycle, taken over a few days from a single direction. Instead, the same picture got recycled in textbooks, posters and documentaries, the same flat disk with maybe a faint ring. If all you ever see is that one frame, you naturally assume the planet is always like that. The misunderstanding here is straightforward. One snapshot was treated like a complete movie. Then comes the real problem, the lack of follow-up. Mars has orbiters and rovers running for years. Jupiter has had multiple missions, Saturn had Cassini in orbit for more than a decade. Uranus, despite being bigger than every rocky planet put together, still has only that one quick flyby. No orbiter parked there to watch the weather change. No probe dropped into the clouds to measure temperatures and composition directly. No slow methodical survey of the rings and moons from close range. From Earth, with observatory mirrors, you're fighting distance. Uranus orbits around 2.9 billion kilometers from the Sun, roughly 1.8 billion miles. Its apparent size in the sky is tiny, just a small disk even in powerful telescopes. You can switch to infrared and use advanced techniques, and scientists do, but the data is still nothing like what you get from a dedicated orbiter sitting in the system and watching day after day. Put that all together and you get at a data desert. Instead of detailed maps of its gravity field, long-term movies of its storms and repeated close passes by its moons, You get scattered telescope snapshots and a brief archive from 1986. A giant planet has less detailed, up-close information than some asteroids we have visited. That is how a world that should feel central ends up feeling optional in your picture of the solar system. You might shrug and say, fine, one planet is understudied. What is the big deal? Here is where the stakes jump. Uranus is an ice giant, and this class of planet is not rare at all. When astronomers look at exoplanets around other stars, they keep finding worlds in the same mass and size range as Uranus and Neptune. So if your picture of Uranus is wrong, your instincts about that whole category are off. You might assume their interiors are simple when they are layered and complex. You might assume their atmospheres are quiet when they can host extreme winds and unusual chemistry. You might assume their magnetospheres are textbook when they are twisted and offset. Those wrong instincts then slide directly into the models scientists build for distant ice giant type worlds. That affects how you estimate their temperatures, how you read their spectra, and how you think about their moons and rings. If you've already decided that an ice giant is basically a dull, cold blue sphere that you can ignore, you are going to underestimate the environments around those planets, including where liquid water and interesting chemistry might exist. The joke, the single washed-out photo, and the long silence after Voyager 2 all work together. They push your attention away from a planet that should be central to how we understand ice giants and exoplanets. And that is before you even get to one of the strangest facts about Uranus, the way it is tilted so far over that it is effectively rolling around the sun on its side, with seasons that last longer than a human working life and climate patterns that break your normal expectations. How do you picture a planet spinning, a ball turning neatly under a lamp, or something doing almost a full sideways flip? Uranus is in that second category. It doesn't lean a little like Earth. Earth's axis is tilted by about 23.5 degrees. Uranus is tipped by about 98 degrees relative to its orbit. That means, depending on how you define up, you can honestly say Uranus is basically rolling around the sun on its side. So instead of a world spinning like a top with a gentle lean, you have a world whose spin axis is almost lying in the plane of its orbit. If you could hover above the sun and watch, you'd see Uranus moving along its path while its poles sweep around in a way that makes every basic diagram you saw in school feel wrong. The North Pole doesn't just tilt toward the sun once in a while, it can end up pointed almost directly at it. Then decades later, the South Pole takes its turn. For a planet this big, around 51,000 kilometers across, about 32,000 miles, that is not a small cosmetic detail. That orientation rewrites how sunlight hits the atmosphere, where energy goes, and how the whole climate system works. So what does that actually do to seasons, if the axis is almost horizontal instead of mostly vertical? On Earth, you're used to a year where the sun's position in the sky shifts over months. Spring, summer, autumn, winter, repeating over and over. On Uranus, one full year is about 84 Earth years, and the tilt turns each season into a huge block of time. Each pole spends roughly 21 Earth years in continuous daylight, then about 21 years in continuous darkness. Think about that pattern. If you stood near the North Pole of Uranus at the start of its long day, the sun would slowly circle above the horizon and never set. Not for years, not for decades. Then after about 21 years, you'd slide into a night that also lasts about 21 years. If you tried to map that onto a human life, you could be born near the start of spring, grow up through a continuous day summer, and not hit the deep, long night equivalent of winter until middle age. For the southern hemisphere, the phases are flipped. Daylight and darkness trade places on that same 84-year clock. This is not just a fun fact. Those long stretches of polar heating and cooling drive atmospheric circulation in a way your Earth-trained intuition does not handle well. On Earth, heating moves slowly back and forth between hemispheres every 6 months. On Uranus, the sun pours energy into one pole for decades, then shifts to the other pole. The equator spends long periods at lower average sunlight compared to a pole in its peak season. That changes where big temperature gradients sit, which latitudes get strong winds, and how deep convection can go. Any model that assumes it should behave like Earth but bigger, or it should behave like Jupiter but colder, is already off target. Now connect that tilt back to Voyager 2. If the axis is lying over like that, then sometimes one pole points almost directly at the Sun. So what do you think happens if your only spacecraft visit lines up with that exact moment? That is what happened in 1986. Uranus was near solstice with its south pole facing the Sun, almost head-on. The Sun was hitting that hemisphere straight on. There was no strong day-night line cutting across the disk from our point of view, just a mostly uniform glow. Voyager 2 flew in, racing through the system at around 15 kilometers per second, roughly 33,000 miles per hour. The cameras looked in visible light at a pole that was evenly lit, with minimal shadowing. Under those conditions, subtle differences in cloud height and structure barely show up. The result was a set of images that looked flat, low contrast, and boring. The atmosphere did not suddenly turn calm for our visit. We simply saw it under the most unhelpful lighting and geometry you could pick during a very specific seasonal phase with 1980s instruments. So the sideways tilt didn't just affect Uranus's weather, it sabotaged our first impression. We visited at a time when the geometry hid the drama. Decades later, as the planet moved along its orbit and the Sun's angle changed, telescopes started to pick up more structure, storms and bands, especially in infrared. But the public image was already locked, based on the least informative season. That raises a bigger question. How do you even tip a planet this massive over by almost 100 degrees without destroying it completely? The leading idea is simple and violent. Early in the solar system's history, when planets were still forming and orbits were less stable, Uranus probably got hit by something big, at least several times Earth's mass. Not an asteroid, not a normal comet, but a protoplanet, a half-finished world. Simulations where you slam a several Earth mass body into a 14.5 Earth mass ice giant at tens of kilometers per second show that the spin axis can be tilted by huge angular angles. The collision dumps enormous energy into the interior. Rock, ice and gas can be stripped off, reaccreted, or mixed. Depending on the angle and speed, the impact can also rearrange the internal layers, leaving the planet with a strange configuration. For example, a shell of conducting fluid in a certain band, or pockets where heat is trapped instead of flowing smoothly outward. So when you look at that 98-degree tilt, you're not just seeing a weird rotation, you're looking at the long-term aftermath of a catastrophic event that likely melted and reshaped large parts of the planet. That same event may connect to other puzzles, like why Uranus has such a low internal heat output compared to Neptune, and why its magnetic field is so tilted and offset. But why does this tilt matter for climate and habitability models right now, not just as an old scar? Because every time you pretend Uranus is just Earth but farther, or a small gas giant, you are forcing the wrong physics onto its atmosphere. A sideways planet with decades-long seasons means the pattern of sunlight over its surface is extreme. Ring shadows sweep across different latitudes as the orientation changes, briefly dimming areas and affecting how energy is absorbed. The warped, offset magnetic field means charged particles hit the upper atmosphere in unusual places, heating specific regions in ways a simple model would miss. Energy balance, cloud formation, wind patterns, even where hazes build up, all follow rules shaped by that tilt. You can't just scale Earth equations and call it a day. You need to account for the geometry, the long-term seasonal cycle, and the way the interior and magnetosphere connect to the atmosphere. If you ignore those, your simulations may look neat on paper, but they will not match reality. And if you then reuse that bad intuition on ice giant exoplanets, the errors spread to other systems. So the sideways world aspect of Uranus is not a trivia note. It is a fundamental piece of why the planet behaves the way it does, why our first visit misled us, and why any serious attempt to understand ice giants has to start by taking that tilt and the impact that caused it very seriously. When you think about Uranus, do you mentally shove it into the same box as Jupiter and Saturn and just call all three gas giants? That label is already steering you wrong. Jupiter and Saturn are mostly hydrogen and helium, basically swollen versions of the Sun without fusion in the core. Uranus is built differently. The best interior models say there's only a thin outer envelope of hydrogen and helium, maybe around 0.5 to 1.5 Earth masses in total. Under that, most of Uranus's bulk is a deep mantle of so-called ices, water, ammonia, methane and similar compounds, adding up to something like 9 to 13 Earth masses wrapped around a smaller rocky core. So in terms of structure, you're not looking at a mini Jupiter, you're looking at a huge pressure cooker of heavy molecules with just a skin of light gas on top. That means when you picture what's inside, your mental image should be closer to a gigantic mixed layer of hot, dense fluids and exotic phases, not an endless column of simple hydrogen. And that shift matters, because it changes how the planet holds heat, how it conducts electricity, and how its magnetic field is generated. Now here's the next twist. What does ice even mean inside a planet like this? When planetary scientists say ices for Uranus, they do not mean frozen white cubes like in your freezer. Deeper inside the planet, pressures can reach hundreds of thousands of times Earth's surface pressure, and temperatures can climb to thousands of degrees Celsius, thousands of degrees Fahrenheit. Under those conditions, water, ammonia and methane behave in ways that sound almost alien. One example is something called superionic ice. In that state, the oxygen atoms in water lock into a kind of solid framework, but the hydrogen ions move around through that framework like a liquid. It's part solid, part fluid, and it can conduct electricity extremely well. Lab experiments that push water to hundreds of gigapascals and thousands of Kelvin show signs of these phases. When you apply that to Uranus, a big chunk of its interior might be this weird, electrically conducting semi-solid fluid. That is a very different environment than a simple gas envelope, and it's exactly the kind of layer you'd expect to help generate a strange magnetic field. So how do we know Uranus is packed with this kind of stuff instead of being mostly gas? One simple clue is its average density. Uranus comes in at about 1.27 grams per cubic centimetre, just a bit denser than liquid water, which is 1 gram per cubic centimetre. Compare that to Earth at about 5.5 and even Mars at around 3.9. Uranus is huge but relatively light for its size. Jupiter, by the way, has an average density around 1.33, but that number is deceptive because almost all of that mass is hydrogen and helium crushed under massive pressure. For Jupiter, low density plus huge size screams gas giant. For Uranus, low density plus strong evidence for heavy elements in the atmosphere pushes you toward a different mix. Lots of water, ammonia, methane, other volatiles, and only a relatively small fraction of pure hydrogen and helium. Compositionally, Uranus is closer to scaled-up comet material and icy planetesimals, the kind of stuff the outer solar system formed from, than to a shrunken-down copy of Jupiter. If you force it into the gas giant category mentally, you miss that. Now take that structural difference and look outward, because most of the exoplanets we've found that are a bit bigger than Earth but smaller than Jupiter sit right in this mass and radius regime. These mini Neptunes and sub-Neptunes often orbit very close to their stars, so they'd be much hotter on the surface than Uranus is, but their bulk properties, mass, radius, likely high fraction of heavy elements, are far more similar to Uranus and Neptune than to Jupiter. So if you look at one of these worlds and casually think small hot Jupiter, you're making a serious mistake from the first second. The way heavy elements mix with hydrogen, the way the atmosphere puffs up or stays compact, the speed at which gas escapes under strong stellar radiation, even what kinds of clouds form and at what heights, all depend on whether the interior is dominated by light gases or by ices and rock. An ice giant analogue will respond differently to heating, differently to magnetic forces, and differently to atmospheric loss than a gas giant analogue. Uranus is your nearby test case for that whole category. Here's the uncomfortable part. For a planet this important as a template, Uranus is one of the least constrained giants we have, because we only had a single flyby and no orbiter. scientists have to build interior models that fit a very limited set of measurements, like mass, radius, rotation rate, and the gravity field data Voyager 2 could collect in just a few hours. Many different internal layouts can match those numbers, different layer thicknesses, different distributions of heavy elements, different temperature profiles. That means there isn't just one standard Uranus model. There's a whole family of models that all technically fit the data, but predict very different things about where the ices sit, how heat moves, and how the conductive layers that feed the magnetic field are arranged. When you then use those Uranus-based assumptions to build your models of exoplanets in the same mass range, the uncertainty goes with them. So misunderstanding Uranus is not just having the wrong trivia in your head. It's injecting error into an entire branch of planetary science. You mislabel it as a gas giant. You ignore the exotic physics in its deep ice mantle. You underestimate how strange its interior really is, and then you project that bad picture onto thousands of worlds around other stars. And that brings us straight into one of the biggest puzzles tied to that interior. Because when you actually measure how much heat Uranus gives off into space, you run into a result that should not make sense for a planet with this structure and this history. How can a planet 51,000 kilometers wide, about 32,000 miles, be almost thermally silent? That is the core Uranus problem. Big planets, especially giant ones, are supposed to leak leftover heat from their formation. They should glow in infrared, giving off more energy than they should get from the sun. Jupiter does this in a big way. Saturn does too. But when you look at Uranus, the numbers barely rise above the incoming sunlight, and some analyses put it almost exactly at balance. For a planet this massive, with this much material under pressure, that is not normal at all. Think about what that really means. Jupiter and Saturn are like low-level infrared heaters, still radiating the energy stored when they formed, plus extra from ongoing slow contraction. You point an infrared detector at them, and you see that they're clearly brighter than they should be if sunlight was the only source. With Uranus, when you do the same energy accounting, you get a result that basically says there is little to no extra internal heat leaking out. Either the interior is weirdly cold or something is blocking that heat from escaping to the top of the atmosphere. So maybe you think, fine, maybe that's just what ice giants are like, maybe this is the standard for that class. Then you look at Neptune and that explanation dies immediately. Neptune is only slightly smaller than Uranus, same rough mass range, same ice giant category, not some totally different kind of object. But Neptune radiates roughly 2.5 times the energy it gets from the Sun. In simple terms, Neptune behaves like a normal giant planet with a strong internal heat source, while Uranus, in the same weight class, acts almost shut down. If you take basic cooling models, give Uranus and Neptune similar starting conditions, and let them evolve over billions of years, you naturally get something closer to Neptune's behaviour, a clear internal heat flow, not a flat, almost zero signal like Uranus. So either Uranus had a very different birth and history, or something dramatic happened later that rewired how its interior moves energy. Two planets that should be siblings, same family, same general design, are acting like opposites in infrared. This is not just an old Voyager-era curiosity. New data is making the puzzle sharper, not solved softer. Observations with the James Webb Space Telescope are giving us high-precision temperature readings in Uranus's upper atmosphere, in specific high-altitude layers. Those measurements show temperatures around 150 to 153 degrees Celsius, roughly 302 to 307 degrees Fahrenheit, in regions that earlier data suggested should be warmer. The trend points to a cooling upper atmosphere over time, not a random fluctuation. If it were just an instrument error from the 1980s, you would expect newer hardware to fix the old numbers and move things back toward normal. Instead, multiple measurements are converging on the idea that Uranus is genuinely underpowered at the top, and that its energy transport from the interior to the atmosphere might be changing on decade scales. That is a hint that something in the way heat moves through the planet, from deep layers up to the region we can sense, is not simple convection. So what could force a planet this big into such a strange thermal state? One of the main suspects connects straight back to the extreme tilt you just heard about. The ancient giant impact. The idea is that early in its history, Uranus was hit by a large protoplanet, at least several Earth masses, coming in at tens of kilometers per second. That collision didn't just knock the planet over, it dumped enormous energy into the interior and rearranged the layers. If heavier material sank in some regions but not others, and if different layers ended up with different compositions, you can get what's called layered or inhibited convection. Instead of one big smoothly overturning interior moving heat efficiently outward, you get stacks of layers that don't mix well. Heat builds up in one region, stalls at a boundary, and only leaks out slowly. The total internal energy can still be high, but the rate at which that energy reaches the observable atmosphere is throttled. In that case, Uranus might not actually be cold inside, it might be hiding its heat under internal stratification that our instruments can't see directly. The same impact that tilted the spin axis could have set up this long-lasting internal structure. You end up with a planet that is both literally sideways and thermally weird, not by coincidence, but because both features come from the same violent event in its past. Why does this one planet's heat budget matter so much beyond trivia? Because the whole way we model giant planet evolution is built on matching observed temperatures and luminosities over time. You take a planet's mass, its composition, its age, then you see if your model predicts the amount of energy it's actually radiating. If the match is good, you trust that model more, and you use the same physics on worlds you can't visit, especially exoplanets. If Uranus refuses to fit the standard playbook, then there are key pieces of physics missing in those models, especially for ice giants. Maybe layered convection is common. Maybe giant impacts routinely reset interiors in ways we haven't fully included. Maybe certain mixtures of water, ammonia, and methane behave differently under long-term pressure than our current lab data suggests. Whatever the missing ingredient is, it affects how big icy planets cool, how they separate heavy elements from light ones, and how their magnetic fields turn on and evolve. And since many of the exoplanets we see fall into this same size range, if you get Uranus wrong, you bake that error into your interpretation of whole planetary systems. You might misjudge which planets are still losing significant heat, how thick their atmospheres really are, and even whether their moons or rings sit in environments that could support interesting chemistry or liquid water. The too cold for its size problem is not just a weird line in a data table. It is a warning that we are missing something fundamental about how these worlds live and change. But here's the twist that ramps the tension. While Uranus looks thermally quiet at the top, when you actually resolve its atmosphere with modern telescopes, you don't see a dead, frozen shell. You see motion, fast winds, changing cloud patterns, storms that appear and fade. So the next question hits hard. If the planet is barely radiating internal heat, how is its atmosphere still this active? And what have we been missing in that so-called boring blue ball all along? How can a planet that barely leaks internal heat still drive winds close to jetliner speeds? That is the next big thing you were never told about Uranus. Under that calm blue-green face, the atmosphere is moving fast. Measurements show winds up to about 900 kilometers per hour, roughly 560 miles per hour in some bands. That puts Uranus in the club of the fastest winds in the solar system. These are not gentle breezes. These are high-speed jets ripping around the planet. Those winds don't just spin in circles for fun. They shear across different latitudes, with some regions running prograde, in the same direction as the rotation, and others slower or even slightly retrograde. As they do that, they move methane-rich air around, stacking and stretching cloud systems. In visible light, you barely see any of that. But in infrared and high-contrast images, you start to pick up subtle bands and isolated storm systems sitting on top of those jets. So the plain ball look you grew up with was not the real atmosphere. It was just the part your eyes and old cameras could pick up. To understand why your brain still sees it as a flat teal disk, you have to talk about methane. Uranus's signature blue-green colour comes from methane molecules in the upper atmosphere that absorb red light and let more blue and green through. That part is standard textbook stuff. What usually gets skipped is that this same methane plus haze particles high in the atmosphere acts like a smoothing filter. It wipes out a lot of the contrast. So when Voyager 2 looked in visible wavelengths, at a south pole lit straight on, the methane layer and hazes did a very effective job at hiding deeper structure. Brightness differences between clouds and a background were small, and the cameras simply weren't sensitive enough to dig out the yet weak signal from the noise. The result, the planet looked like a nearly featureless cyan disk. Underneath there were still vertical motions, likely small storms and banded flows, but you were effectively looking at a stormy scene through a dirty window, and the window won. Modern instruments changed that. Large ground-based telescopes like Keck, using adaptive optics and infrared filters, started to show more. The Hubble Space Telescope, free from Earth's atmosphere, added better visible and near-infrared data. And then the James Webb Space Telescope pushed it even further, especially in the near-infrared, where methane absorption and thermal emission highlight different layers. In those wavelengths, Uranus is not quite at all. You see bright compact storms, likely regions of upwelling, where clouds reach higher and reflect more sunlight. You see a polar cap that changes with time, brightening and fading as the seasons slowly shift. You see discrete cloud features that appear, move with the winds, distort and disappear over periods of days to weeks. JWST also brings the rings and deep atmospheric bands into sharp relief, confirming that this planet's environment is active, just not in the part of the spectrum your eyes are tuned to. So you go from a single bland image in a schoolbook to a time series of a dynamic atmosphere, and that forces a mental reset. Uranus is not a frozen static balloon. It is a system where sunlight, internal processes, chemistry and rotation all interact. Even if the measured internal heat flux is low, there is still enough energy from both the sun and whatever internal sources remain to drive serious weather, especially when that energy is distributed in such an extreme way by the 98-degree tilt. That tilt is the next key piece here. Because Uranus's axis is so far over, its atmospheric circulation is not locked into a simple permanent pattern. Over its 84-year orbit, the point on the planet directly under the Sun, the sub-solar point, crawls from one pole down to the equator and up to the other pole. Each phase lasts many years. That means the belts and zones you see at one time are not necessarily what you'll see a few decades later. As the sunlight shifts, polar hoods, those bright regions near the poles, can appear, strengthen, and then fade. The latitude where storms are most common can migrate. Dark bands and bright bands can change thickness. Some models suggest that the entire circulation cell structure, the big overturning loops of air that move heat poleward or equatorward, may reorganize over these timescales. Voyager 2 caught Uranus at one very specific point in this slow cycle near southern summer. Modern telescopes, spread over years, are finally watching the system as it creeps toward different seasonal configurations. That matters because if you only ever sample one season of an 84-year climate cycle, and you do it with 1980s tech, you will absolutely get the wrong general picture. That is exactly what happened. We took one look, under bad geometry and limited wavelengths, and silently generalized it to "this planet is bland." Now, as we add multi-decade, multi-wavelength coverage, that simple verdict is falling apart. So why did you hold on to the idea that Uranus was dead or boring for so long? It's not because the planet lacks motion, it's because your view was constrained. Visible light only, at one season, with instruments that couldn't see faint contrasts, gave you a static ball. No deep shadows, no obvious storm spots like Jupiter's Great Red Spot, no ring system blazing like Saturn's. All the cues that would signal dynamic to a casual viewer were missing. Once you add infrared, higher resolution, and repeated observations, that illusion collapses. You realize the misunderstanding was never in the physics of Uranus, it was in the way we looked at it. Wrong wavelengths, wrong time, and then no follow-up mission. The planet itself never signed up to be boring. We just never bothered to check properly. And this is where the tension ramps again, because the atmosphere is not the only system that refuses to fit your textbook template. If the winds, storms, and seasons already break your expectations, the magnetic field goes even further off script. Uranus does not have a neat, centered, almost aligned field like Earth. Its magnetosphere is tilted hard, offset from the center, and spinning in a way that twists space around it into shapes that are anything but standard. If the air above those teal clouds is already this strange, the invisible field threading through that space is on another level entirely. How do you deal with a planet whose magnetic field doesn't even line up with its own body? On Earth, the magnetic field is pretty tame by comparison. The magnetic poles wander, but the main dipole is roughly centered inside the planet and tilted by only about 11 degrees from the rotation axis. You can draw a simple bar magnet through the middle of Earth and be close enough. Uranus does not let you do that. Its main magnetic dipole is tilted by almost 60 degrees relative to its spin axis, and the center of that magnet is shoved off from the planet's center by about 1/3 of Uranus's radius. Put that in concrete terms, if you tried to do the same thing to Earth, it would be like taking the internal magnetic bar and sliding it so far that the midpoint of the magnet sits under northern Canada instead of at the core. Now spin that lopsided magnet once every 17 hours or so, because that's roughly Uranus's rotation period. The result is a magnetic field that swings and wobbles through space in a very asymmetric way, dragging its magnetosphere, the bubble carved out of the solar wind, into a constantly changing, twisted shape. That weird geometry hits the auroras first. On Earth, you're used to auroras clustering near the magnetic poles, which roughly line up with the geographic poles. You get oval-shaped auroral zones that stay in fairly predictable regions. On Uranus, with the field offset and tilted by nearly 60 degrees, the places where magnetic field lines plunge into the atmosphere are not confined to neat circles around the spin poles. As the planet rotates, those field lines sweep across different latitudes and longitudes. So instead of stable auroral ovals, you get patterns that move and morph as the whole skewed magnet system spins inside the solar wind. Recent observations with the James Webb Space Telescope have been able to map these auroras in 3 dimensions. Webb tracks how charged particles from the solar wind follow those twisted field lines down into the upper atmosphere and dump energy there. The data show ions being heated to hundreds of degrees Celsius in specific regions far above the cloud tops as those magnetic funnels focus power into the ionosphere. And that ionosphere, the charged upper layer of the atmosphere, is not just a smooth, boring shell. Webb and other high-resolution observations reveal that Uranus's ionosphere has vertical structure, distinct layers stacked at different altitudes. You see regions where the density of charged particles peaks around 1,000 kilometers above the visible clouds, and other regions where the temperature spikes much higher up, around 4,000 to 5,000 kilometers. Those layered peaks are not random. They line up with where the scrambled magnetic field is strongest or where field lines connect efficiently to the solar wind. In other words, the magnetosphere is sculpting the vertical structure of the ionosphere. That tells you the field is not behaving like a simple centered dipole. You have complex current systems, tilted and offset field lines, and probably contributions from higher-order magnetic components, all superimposed on the basic dipole. Why does that matter beyond Uranus is odd? Because that kind of offset tilted field is exactly what you expect if the magnetic dynamo, the region where moving conductive fluid generates the field, is not a big uniform core like Earth's, but a shell or a set of layers in an ice giant interior. Remember the ices deep inside Uranus? Water, ammonia, methane under extreme pressure and temperature, probably forming exotic phases like supraeonic ice. If the electrically conducting region lives in a relatively thin shell or in uneven layers instead of filling the whole interior, the field you get naturally ends up offset and strangely shaped. Now link that to exoplanets. A huge number of known exoplanets fall into the same mass and radius range as Uranus and Neptune. Many of them are much closer to their stars, which means they're being blasted by intense stellar winds and radiation. For these worlds, the magnetosphere is not an optional detail. It controls how atmospheric particles escape, how much of the upper atmosphere gets heated or stripped, and what sort of radio and auroral signals we might be able to detect from far away. If you can't explain Uranus's field, this nearby, relatively accessible example of a tilted, offset magnetosphere produced in an ice giant interior, you're not ready to interpret magnetospheres around those hot Neptune-like exoplanets. You won't know how to read their radio emissions properly. You won't know how to estimate atmospheric loss rates correctly. You won't even know what geometries to expect when you model how their fields interact with their stars' winds. This feeds directly into habitability discussions too. When people talk about whether a world can hold onto an atmosphere or protect a surface or a moon from high-energy particles, they often reduce the question to, does it have a magnetic field, yes or no? Uranus shows you why that is way too simple. It clearly has a magnetosphere, but it is so offset and skewed that the shielding is patchy and time-dependent. Different regions of space around the planet will be more or less exposed as the field rotates and flexes. That changing shield shapes where high-energy particles can penetrate, where auroras heat the upper atmosphere, and how energy gets injected into any nearby moons or rings. If you transplant that kind of system to a closed exoplanet with strong stellar wind, you get a very complex, maybe even chaotic interaction zone. Some parts of the atmosphere might be strongly eroded, others might be better protected. Some long-term orbits for moons could be bombarded, others less so. So the smarter questions are not, does the planet have a magnetosphere? They're, what shape is it? How far is it offset? Which latitudes does it connect to? And how does that connect down into the atmosphere and out into the plasma environment? Uranus forces you to ask those questions because the simple Earth-style pictures just don't work. Its crooked magnet is not just a curiosity. It is a live example of the kind of magnetic complexity you should expect in many ice-rich worlds across the galaxy. And once you take that seriously, you're pushed into a harsher realization. If the field is this tangled and the auroras and plasma environment are this dynamic, what does that mean for the material close in? The rings and the small moons moving through this distorted electromagnetic bubble. You've been quietly told for years that Uranus's rings are faint, minimal, almost not worth thinking about. But in a field this strange, those invisible rings are part of an active system, not a decoration. The next step is seeing how wrong your mental image is there too. How can a planet you were taught to see as a plain blue ball actually be wrapped in a whole set of rings that almost never get mentioned? Saturn grabbed your attention with bright, wide, icy rings, and everything else got mentally downgraded. But Uranus is a ringed world too, just in a stealth mode version. It has at least 13 known rings, narrow, dark bands orbiting between about 38,000 kilometers and 98,000 kilometers from the planet's center, roughly 24,000 to 61,000 miles. Many of those rings are only a few kilometers wide, razor thin on a cosmic scale, and they're made of very dark material, probably coated in carbon-rich stuff that reflects only a small fraction of the sunlight that hits it. So instead of a bright, flashy disk like Saturn's, Uranus carries a tight, dim halo system, composed of narrow rings and dusty bands that almost vanish in normal light. That doesn't mean they're unimportant. They still shape how dust moves, how small moons interact with debris, and how the planet's gravity and magnetosphere sculpt its surroundings. But because they don't light up the sky the way Saturn's do, they slip past your attention and probably past your mental picture of the solar system. Why were you never really shown them? Part of the answer is straight up observational bias. Voyager 2 nearly missed them. When the spacecraft flew past Uranus in 1986, the team mostly saw the rings in a special geometry, with the sun behind them, so the ring particles scattered light toward the camera. In that backlit setup, even very dark material can show up, because you're seeing sunlight passing through and around the particles. But at most other angles and wavelengths, Uranus's rings are extremely faint, orders of magnitude dimmer than Saturn's bright icy ones. If you look at Uranus in normal visible light, from Earth, without extreme contrast work, those rings barely register. So your school posters and textbook illustrations defaulted to Saturn as the ringed planet, and Uranus as plain ice giant with maybe a faint ring if we have room to draw it. The reality is, the second world has a complex ring system too, it's just subtle and easy to miss. Once again, modern telescopes broke that old picture. Infrared imaging from James Webb took the Uranian rings and pulled them out of the noise with sharp detail. In Webb's near-infrared views, you can separate individual narrow rings, see their thickness, and pick out structures in the more diffuse outer rings. Some observations show slight brightness variations, clumps, and asymmetries, which are exactly what you'd expect if tiny moonlets are embedded in the rings, stirring them up and shaping their edges. That tells you the rings are not just leftover rubble sitting there quietly. They're part of an active debris system, where dust is constantly being created by collisions, knocked around by electromagnetic forces, and swept up or confined by small moons. Ring particles smash into each other, chip off smaller fragments, and slowly spiral inward or outward. The system evolves, even if the changes are slow on human timescales. Then you get to the really recent twist, the discovery of a new mini-moon hiding near the inner rings. In 2025, analysis of JWST data revealed a previously unknown inner moon, currently labelled S/2025U1, only about 10 kilometres across, around 6 miles. It orbits just inside the dark inner rings. That location is not random. Small moons at the edges of rings often act as shepherds, their gravity nudging ring particles, keeping narrow rings sharp and preventing material from spreading out too fast. So now, instead of a simple picture, planet plus one vague ring circle, you have a more crowded, dynamic scene. Narrow rings, dusty outer bands, and small moons weaving through them. Some known, some probably still hiding below our detection limits. That's an entire hidden zoo of interactions that your basic school diagrams completely skipped. The more closely we look, the more it starts to resemble a scaled down, darker, and more chaotic cousin of Saturn's ring-moon environment. Why should you care about a few dim rings and a 10-kilometre moonlet? Because ring systems are not just ornaments, they're records. Each ring particle is a tiny piece of history, a fragment of a shattered moon, a chunk of material from a collision, or dust knocked loose by micrometeoroids over billions of years. Their sizes, compositions, and orbits hold clues about when impacts happened, how the moons formed, and how much debris has been flowing through the outer solar system. If the material is very dark and carbon-rich, that points to certain types of parent bodies. If the rings are narrow and sharply edged, that hints at active confinement by moonlets. If there are thick, dusty components, that suggests ongoing grinding and bombardment. All of that ties back into the bigger story. Was there a giant impact that helped create this system? How often do objects collide out here? And how stable are these rings over long times? By labelling Uranus as basically ringless, or ring-light, you've been ignoring one of the best archives of that history. You lose a key data source on how debris moves in a tilted, offset magnetosphere. You lose information about how small bodies behave under Uranus's odd gravity and electromagnetic field. You also miss a chance to compare ring systems across planets and ask, why are Saturn's rings bright and icy, while Uranus's are dark and narrow, and what does that say about their origins? And that brings up the next escalation in this story. If the dark, faint rings are already this revealing, what about the larger solid worlds orbiting farther out? The big moons of Uranus don't just sit outside this system as passive rocks, they move through the magnetosphere, they feel the dust environment, and some of them show signs that their interiors may be far more active than we used to think. If the rings are an ignored archive, the moons are an ignored frontier, and together they point at something even more dramatic, possible hidden oceans in one of the most neglected regions of the solar system. How does the system everyone wrote off as too small, too cold, too far suddenly show signs of hiding oceans? That's the situation with the big moons of Uranus. You probably learnt their names once, Miranda, Ariel, Umbriel, Titania, Oberon, then forgot them immediately because they were sold as generic ice balls, cratered and dead. But look at their actual cheers. Their radii run from about 470 kilometers up to around 1,580 kilometers, roughly 290 to 980 miles. That puts the largest of them in the same ballpark as bodies we already suspect or know have subsurface oceans elsewhere, and the smallest one still large enough for serious internal physics. For decades, though, the default view was simple. They're too small and too far from the sun to stay warm inside, so they must be frozen solid. Voyager 2's quick flyby in 1986 gave us a handful of close images, enough to see that the surfaces were icy and cratered, with some weird patches here and there. Then the system was basically put on pause. No orbiter, no radar mapping, no gravity flybys to measure their interiors. So the cold dead ice ball label stuck. Not because of strong evidence, but because nobody bothered to interrogate it. Now the story is flipping. When scientists started running more detailed models of these moons' orbits and how they wobble, called librations, a different picture came out. The key idea is tidal heating. As a moon orbits a massive planet like Uranus, the gravity field stretches and squeezes it a little. If the orbit is not perfectly circular, that flexing changes as the moon moves closer or farther away. If moons get locked into orbital resonances with each other, where their orbital pole periods line up in simple ratios, that constant gravitational tugging can stay strong over very long times. That repeated flexing generates heat inside, just from friction in the rock and ice. It's the same basic mechanism that keeps Jupiter's moon Io volcanic and helps sustain Europa's ocean. For the Uranian moons, models show that in the past, when resonances were stronger or orbits slightly different, tidal heating could have been intense enough to melt parts of their icy interiors, forming global or regional layers of liquid water and slushy material under the crust. Even if that heating later dropped, those layers don't freeze instantly. They can persist for hundreds of millions of years, maybe longer. That immediately breaks the old too small, too cold to matter narrative. If the orbits and resonances are right, you don't need a lot of sunlight to run an ocean. You need internal flexing and the right mix of salts and antifreeze compounds in the water. The Uranian moons tick more of those boxes than we used to admit. Miranda is the one that really forces you to stop and rethink. It is tiny by moon standards, only about 470 kilometers across, 290 miles, with surface gravity less than 1% of Earth's. If any body deserved the "just a frozen rock" label, it was this one. But when Voyager 2 flew past, its cameras showed something that did not match that simple story at all. Miranda's surface is shredded with enormous canyons up to about 20 kilometers deep, around 12 miles, and strange patchwork regions where one type of terrain seems to be sliced out and stuck next to another. That kind of extreme localized geology is hard to explain if the moon was always just cooling off passively. It points towards serious internal activity, big upwellings of warmer material, and crustal motion. For a while, people treated Miranda as a one-off oddity, a weird case that didn't mean much for the rest of the system. But newer work, combining improved orbital models and better understanding of tidal heating, has gone further. Some studies now argue that Miranda may still have a thin subsurface ocean today, insulated under the crust. If that's true, then this small distant moon, almost 3 billion kilometers from the sun, about 1.8 billion miles, could still be warm inside with liquid water sitting under fractured ice. That takes it from cratered ice rock to possible ocean world in one step. For the search for habitable environments, that's a big mental shift. It means you can't stop at the gas giants and their famous moons. You have to include small, previously ignored bodies in tilted, complex systems like Uranus's. Ariel is the next major warning that you underestimated this system. Ariel is larger than Miranda, and its surface shows long trenches, grooves, and areas that look relatively young, meaning fewer craters and more signs of recent resurfacing. Some of those features line up with the idea of material rising from below and stretching the crust, rather than just being sculpted by impacts from outside. Spectral data also show signs of carbon-bearing material on Ariel's surface. One interpretation is that you have a combination of internal upwelling and material being delivered from outside, possibly from dust and the ring environment. One recent study connects the observed structures and composition to a subsurface ocean layer that either still exists or froze not that long ago in geologic terms. If that holds up, Ariel doesn't just join the list of interesting moons, it enters the same conversation as Europa, Enceladus and Titan. Worlds you're used to hearing about when people talk seriously about ocean worlds. You end up with at least 2 moons in the Uranian system, Miranda and Ariel, with credible arguments for past or present subsurface oceans and hints that tidal heating and complex orbital histories played major roles. Umbriel, Titania and Oberon also show signs of internal differentiation and possible past activity, though we know much less about them. The point is, the all-dead ice balls picture is collapsing. In its place, you're getting a system where multiple moons may have hosted, or may still host, layers of liquid water mixed with salts and ammonia under insulating ice shells. So what does that mean for where you draw the line on habitability? If you ignore Uranus, you ignore an entire family of potential ocean worlds. At least some of them sit in a magnetosphere that can deliver energy and charged particles to their surfaces, and possibly into their interiors through induction. Their orbits and tidal histories can maintain heat far from the Sun. If even one of these moons still has a long-lived, salty, energy-rich ocean, then the outer solar system's habitable real estate extends further and comes in more forms than you were taught. And here's where the tension jumps again, because if the big moons are this promising, the strangest, most extreme one in the set, Miranda, becomes even more critical. You're dealing with a tiny world with ridiculously low gravity, absurdly tall cliffs, and Frankenstein-looking terrain that might still be warm inside. If you want to test how far you can push the idea of an active ocean world in a harsh environment, Miranda is the edge case that will either break your theories or expand them. Miranda doesn't just bend the rules for a small moon, it looks like it tore them up and taped them back together. Its surface gravity is only about 0.008 g, less than 1% of Earth's. You could jump off a cliff there and fall in slow motion. But the cliffs themselves are insane. Verona Roops may rise something like 20 kilometers, around 12 miles from base to top. On a body this small with gravity this weak, you're looking at vertical relief that feels completely out of scale. Then you zoom out and the terrain doesn't look like a normal old beaten up ice ball. You see huge jumbled regions, where it honestly looks like blocks of crust have been cut out, shifted, and dropped back down in the wrong order. Cratered plains butt up against strange, grooved regions, and nothing lines up cleanly. If Miranda had just cooled, cracked, and taken random impacts, you'd expect a simpler pattern. Old craters, maybe a few fractures, nothing this patchy and chaotic. The level of tectonic disruption here is way too high for a tiny moon that's supposed to be geologically boring. Those bizarre ovals on the surface, the coronae, well, are the next clue that something deep was going on. These giant, roughly oval patches are not impact scars. The leading explanation is that they formed when warmer material from inside the moon pushed upward, deforming and breaking the crust. That kind of upwelling needs an energy source. With almost no sunlight to work with, the power has to come from inside, and the best candidate is tidal heating. In the past, Miranda likely sat in stronger orbital resonances with other Uranian moons, getting pulled and released on a regular cycle as it went around Uranus. That constant flexing in a body made of ice and rock turns mechanical energy into heat. Models show that under the right resonances, you can pump enough heat into a small moon like Miranda to partially melt its interior. Once you have pockets or layers of liquid, things get even more interesting. You can form a subsurface ocean, drive convection, and feed that warm material upward to create those coronae and deep fractures. This is not passive geology, this is active reshaping driven by tides in the gravity field of a sideways planet. Now the question is, did all of that completely shut down, or is there something left? A wave of studies in the 2024 to 2026 window argues that Miranda might still have a thin, subsurface ocean today. The argument doesn't come from direct radar soundings. We don't have an orbiter there yet. It comes from what you don't see on the surface. If the interior had fully frozen and contracted, you'd expect a global pattern of certain tectonic features, widespread compressional faults and ridges as everything shrank. Instead, the current surface doesn't match that full contraction signature. That gap hints that not all of the interior has gone rigid and cold. Some layer at depth may still be warm and ductile, able to flow slowly instead of snapping. If that layer is at the right temperature and composition, it can be at least partially liquid, a briny or ammonia-rich ocean trapped under the ice. So you end up with a tiny moon, almost 3 billion kilometers from the Sun, about 1.8 billion miles out, that might still be warm enough inside to host liquid water. That's not how you were told the outer solar system works. For a long time, the easy way to handle Miranda was to point at it as a weird exception, a one-slide curiosity in a lecture. Look at this oddball, no idea what happened here. Then move on. That framing is now breaking. Once you factor in tidal heating, layered interiors, and the possibility of long-lived internal oceans, Miranda stops being the lone freak and starts looking like the extreme end of a broader pattern in the Uranian system. The real mistake wasn't noticing that Miranda is strange, it was assuming the rest of Uranus's moons must be simple by comparison. This is where Miranda kicks the door open on exomoons too. If a moon this small, with this low gravity, this far from its star, can sustain major tectonic disruption and maybe even hang on to an ocean, you have to rethink what's possible around ice giants in other systems. Many exoplanets we have found are in the Uranus-Neptune range. It's reasonable to assume at least some of them have moon systems. If their moons feel strong tides and live inside complex magnetospheres like Uranus's, you could get Miranda-style outcomes. Small bodies with surprisingly active interiors and liquid layers. If you underestimate Miranda, you underestimate that entire category. You'd look at a distant ice giant, assume its moons are non-factors for habitability, and move on. When in reality, those moons might be where the real action is, deep under ice, powered by tides and electromagnetic energy. Miranda is basically a warning label saying, your size and distance rules are too strict, you're missing things. And if the smallest, most shredded moon in the set is already forcing you to widen your search, the bigger ones sitting farther out raise a different kind of red flag. Their surfaces don't even follow the basic brightness and patterns you'd expect from standard space weathering. Parts that should be darkened by plasma and particles are unexpectedly bright. And the dark sides don't line up with the simple geometry you use at Jupiter and Saturn. If Miranda blew up your assumptions about internal activity, the next group of moons is about to blow up your assumptions about how surfaces age in a magnetosphere like Uranus's. How do you screw up something as basic as which side of a moon should be darker? Start with what you'd expect. The big Uranian moons are tidally locked. One face always looks at Uranus, the other always looks away. As they orbit, each moon has a leading side, the side facing forward in its orbit, and a trailing side, the side facing backward. At Jupiter and Saturn, magnetospheric particles slam into the trailing hemispheres more, so those sides get darker and more processed over time. Simple geometry, simple rule, dark side equals trailing side. So you'd carry that rule over to Uranus without thinking. Same basic idea, big planet, magnetosphere, tidally locked moons. But when Hubble and other telescopes started taking ultraviolet data of moons like Titania and Oberon, the pattern was wrong. In some cases, the trailing sides were actually brighter than the leading sides. The part of the surface that should have been roughened and darkened by the charged particles looked cleaner. That contradicts the standard model of how magnetospheric weathering is supposed to work. If the rule fails, either the magnetosphere is behaving in some very odd way, or something else is modifying the surfaces. The explanation scientists landed on pools in another part of the Uranian system you'd probably ignored: dust. These moons orbit in a region where there are rings, smaller moonlets, and a constant trickle of impact debris. The leading hemispheres are ploughing forward through that environment like the front of a car on a highway. They hit more dust, more tiny particles, and more ejecta from micrometeoroid strikes. That material doesn't just bounce off, it sticks, coats, and slowly builds up a layer. If that dust is dark, carbon-rich stuff, it will lower the albedo of the leading side, making it look duller and darker. Meanwhile, the trailing side gets less of that direct dust flux and can actually end up looking comparatively cleaner and brighter, even while magnetospheric particles are hitting it. This is the dust shielding idea. Dust hitting the leading side shields the trailing side from looking as processed, not by blocking particles, but by dominating the surface makeover on one hemisphere. Now add one more factor: resurfacing from below. On a moon like Ariel, you don't just see old craters and a simple colour pattern. You see long trenches, grooves and areas that look geologically young. You also see signs of carbon-bearing material on the surface. That combination points to a three-way competition. Dust and impact ejecta arrive from outside. Plasma and energetic particles from Uranus's tilted magnetosphere hit from above. And warm material, possibly carrying volatiles and carbon compounds, may be rising from below or freezing out near the surface. If Ariel has, or recently had, a subsurface ocean, or at least a warm, ductile layer, then cracks and faults can open pathways from the interior to the surface. That lets subsurface fluids or slurries bring salts and carbon out, changing chemistry and reflectivity. So when you see a patch that's darker or richer in carbon, it's not just space dust. It could be a mixture of exogenic material from the environment and endogenous material from an interior layer. That's not just a paint job, that's a geochemical signal. This ties straight back into energy budgets. If internal activity is still capable of resurfacing parts of Ariel, that implies stored heat and possibly ongoing tidal or radiogenic heating. The presence and distribution of carbon-rich areas can tell you where external dust dominates and where internal processes are punching through. When you integrate all that, the colour pattern becomes a map of both external bombardment and internal dynamics. Here's where the stakes really climb. Planetary science uses crater counting and surface brightness as tools to estimate ages. You look at how many craters are on a surface, combine that with impact rate estimates, and get a rough age. You also use colour and albedo patterns to guess how long a region has been exposed. If you've got the geometry of darkening processes wrong, which hemisphere should be more weathered by plasma, where dust is accumulating, how often resurfacing resets the clock, then your age estimates are off. That cascades quickly. If you misjudge which terrains are old and which are young, you miscalculate when an ocean might have frozen, when tectonics shut down, and how long internal heating stayed strong. You could decide an ocean died out billions of years ago when, in reality, parts of the interior stayed warm much longer. Or you might miss signs that certain hemispheres have been resurfaced more recently by ocean-related processes because you're incorrectly blaming the brightness on just dust patterns. So a simple mistake about which side looks darker turns into a deeper error about the timelines of these moons. You lose track of how long they stayed geologically active. You underestimate the total duration of possible habitable conditions in subsurface oceans. And once again, if you transfer those wrong instincts to exomoons in other systems, you misread their surfaces and their histories too. All of this is happening because your data set for Uranus's moons is built on one fast flyby and then scattered telescope snapshots. You're trying to reconstruct billions of years of thermal and orbital history from a tiny sample. The moons themselves are basically telling you through gravity, colour and crater patterns, you're not modelling us right. And the root of that, just like with the planet, comes back to a brutally simple fact. We rushed past once, then never went back. If a single quick encounter can leave you this wrong about which side of a moon is darker and how long it may have had an ocean, what else did you lock in incorrectly from that one pass by Uranus in 1986? That question takes you straight to the next problem, the way one 5-hour stretch of data during one seasonal configuration quietly froze the story of an entire planetary system in your head for almost 4 decades. How much do you really know about a planet when your entire close-up encounter lasted about 5 hours? That's the core problem with Uranus. Voyager 2 crossed the most data-rich part of the Uranus system at tens of kilometers per second, grabbed what it could, and then it was gone. One fast pass during one season, at one viewing angle, for a world that takes 84 Earth years to go around the Sun once. If you tried to judge Earth's entire climate and geology from a single high-speed pass over Antarctica, you'd call that ridiculous. That is basically the sample we have for Uranus. During those hours, the spacecraft did everything it could. It mapped the magnetic field, it snapped images of the planet, rings and moons, it took spectra of the atmosphere and environment. But there is a hard limit to what you can do when you're diving through an entire planetary system in a fraction of a day. You don't get to see how storms grow and die, you don't see seasons shift, you don't watch how the magnetosphere reacts when the solar wind changes, you just freeze one configuration in time and hope you can reconstruct the rest later with models. Then add the technology ceiling of the 1980s. Voyager's cameras and spectrometers were excellent for their era, but you can't pretend they match the sensitivity, resolution or wavelength coverage of Hubble, Keck or JWST. In visible light under that awkward south pole facing the sun geometry, the cameras simply could not pick up subtle cloud contrast or faint structure. The methane haze washed out brightness differences. The ring dust was so dark and faint that it only really popped when the sun was behind it, making the particles scatter light forward into the camera. So what the public saw were the clearest visible images, which showed a smooth cyan disk, a faint ring, and a couple of small moons. The more nuanced data, the spectra, the magnetometer readings, the lower contrast imagery, never made it into your mental picture. And the wavelengths where Uranus really starts to look structured, in the infrared, were mostly out of reach for Voyager's instruments. The tools we had were not bad, they were just limited, and the viewing conditions amplified those limits. Here's the big difference between Uranus and the other outer giants. Jupiter and Saturn both got dedicated orbiters later. Galileo and Juno rewrote the Jupiter story. Cassini transformed Saturn from a ringed gas giant into a whole ecosystem of storms, rings, and ocean moons. Those missions corrected, expanded, and sometimes totally overturned the first impressions from the Voyager flybys. The public image moved with the data, because new pictures and discoveries kept coming in. Uranus did not get that second act. No orbiter, no lander, no probe dropped into the atmosphere. The boring, cold, pale snapshot from 1986 stayed in circulation, unchanged, even while professional astronomers quietly updated their internal files using ground-based and space telescope observations. The science moved on, but the popular image stayed frozen. In your head, Uranus never evolved past that old Voyager frame, because nothing as dramatic as Cassini at Saturn came along to push it out. The cost of that gap is huge. We still don't have precise multi-pass gravity field measurements to lock down Uranus's internal structure. We don't have in situ magnetic and plasma data taken at different seasons, when the pole pointing at the sun changes. We have not flown past Miranda, Ariel, Titania, or Oberon again to refine their shapes, mass distributions, and surface details. Every time you see a phrase like, "We think Uranus's interior is," or "models suggest the moons may," there's a good chance that statement is resting on one slice of 1986 data, plus a lot of computational guesswork. Simulations are powerful, but they need constraints. When your gravity field is only loosely known, many different interior configurations can fit the same data. When your magnetosphere has only been sampled once, in one seasonal state, you can't be sure how it behaves when the poles swap from light to dark. When your only close images of the moons are from one geometry, you could be missing entire classes of features on their far sides. You can't just simulate that away and pretend the uncertainty isn't there. The error bars are real. So when someone says, Uranus probably has X structure, or its moons probably cooled in Y way, that probably carries a lot more weight than you might think. Compared to Jupiter and Saturn, where multiple missions and repeated measurements pin things down, Uranus is still in the "we're doing our best with scraps" category. The mismatch between how confident the old story sounds and how thin the original dataset is, that's the problem. This is what misunderstanding by neglect looks like. There was no big argument about what Uranus is like. There was no dramatic controversy that kept it in the news. There was just a slow fade. One quick visit, a set of images that look dull, a whole system mentally filed under done, and then decades where funding and mission priorities went elsewhere. Uranus was basically left on read by humanity, a message opened but not answered. Meanwhile, telescopes kept quietly finding hints that the old picture was wrong. Storms in infrared, changing polar hoods, complex auroras, faint rings with structure, moons that might be hiding oceans. You now have a situation where the most up-to-date view of Uranus among specialists looks nothing like the flat, dead world that lives in public imagination. And that gap, that lag between data and perception, is exactly what you have to close if you want to stop using a bad mental model for one of the key planet types in the galaxy. So the next logical step is obvious. If the one fast flyby mislabeled Uranus for nearly 40 years, what happens when you finally point the best modern telescopes at it and start peeling away the teal haze across multiple wavelengths? The answer is the planet starts fighting back against its own stereotype, and it does it fast in infrared high definition, with rings, storms, auroras, and even new moons showing up on your screen. How fast can a planet's reputation change once you finally point the right tools at it? In just a few years, the James Webb Space Telescope has taken Uranus from a blurry teal dot to a detailed, structured world. In infrared images, you now see the full ring system clearly separated from the planet, a bright polar cap, distinct bands wrapping around the globe, and individual storm features standing out against the background. The disk isn't smooth anymore. It has texture, structure, and contrast that we simply could not resolve before. The polar region especially jumps out. Instead of a vague bright area, you see a defined polar cap, with sharp boundaries between the bright region and the darker mid-latitudes. Within that cap, storms and cloud features pop up as localized bright spots. Bands closer to the equator show changes in brightness that track with jet streams. The rings show up as multiple distinct arcs, not one fuzzy stripe. When you line these infrared views up against the old Voyager frames, it's obvious how much detail was missing. You were looking at a low-resolution thumbnail for decades. Now you're finally seeing something close to the real thing. Webb is not just making prettier pictures, it's filling in missing physics, starting with the auroras. For the first time, instruments on JWST have been able to map Uranus's auroras in 3 dimensions. That means tracking where, in latitude and longitude, the emissions appear, and also how high above the cloud tops the energy is being dumped. The data show charged particles spiraling down along those twisted, tilted magnetic field lines and hitting specific regions high in the atmosphere. From those observations, scientists can reconstruct temperature profiles with altitude. In some of those auroral regions, temperatures reach around 426 Kelvin, about 150 degrees Celsius, roughly 302 degrees Fahrenheit, far above the cloud tops. That tells you that the magnetosphere is pumping serious energy into the upper atmosphere, in narrow channels. It also shows vertical flows of energy that do not match older, simpler models, where the ionosphere was treated as a smoother, more uniform layer. The field is not just crooked on paper, it's actively reorganizing how heat and charged particles move with height. Then there's the long-term temperature story. Multiple JWST campaigns, separated in time, are converging on the same result. Uranus's upper atmosphere is cooler than older measurements suggested. That is not just a calibration quirk. When you consistently see lower temperatures, with different instruments and different teams, you're picking up an actual physical trend. The upper layers of the atmosphere appear to be cooling as the years go by. That means Uranus's energy balance is changing on decadal timescales while we're watching. Something about how heat is transported from the interior to the upper atmosphere, or how energy from the sun and the magnetosphere is absorbed and radiated, is shifting. Maybe internal heat is getting trapped more effectively by layered convection. Maybe changes in solar activity and the planet's extreme seasons are altering how much energy reaches and stays in the upper atmosphere. Whatever the detailed cause, the planet is not in a static thermal state. It is evolving measurably over the span of a human career. At the same time, Webb is sharpening our view of the rings and the objects embedded in them. The infrared images separate individual narrow rings with high clarity, showing their thickness and brightness variations along their arcs. The dusty outer rings, which were just faint smudges before, now show structure, with hints of clumps and asymmetries. Those variations are exactly what you'd expect if small moonlets are stirring the material and confining the rings. That expectation is backed up by actual discovery. In 2025, analysis of JWST data revealed a previously unknown inner moon, temporarily labelled S/2025U1, roughly 10 kilometres across, about 6 miles. It orbits just inside the dark inner rings. Its existence is a direct signal that Uranus's ring moon system still has surprises at kilometre scales, even in a region we thought we had already catalogued reasonably well. If one moonlet like that turns up quickly in new data, there could easily be more hiding in the noise, waiting for deeper analysis. Webb sensitivity also allows better tracking of how the magnetosphere connects to the upper atmosphere and rings. By watching auroral emissions and ring brightness changes at different wavelengths, you can see how charged particle populations shift, how currents flow, and how chemistry in the upper atmosphere responds. That starts to connect the dots between the crooked field, the patchy auroras, the layered ionosphere, and the dusty rings. Uranus stops being a collection of separate oddities and starts looking like a tightly coupled system, where field, plasma, atmosphere, rings, and moons are all interacting. All of this adds up to a simple fact: you are living through the moment when Uranus is moving from background object to frontline laboratory. For decades it sat there, under-observed and under-discussed, while Jupiter, Saturn and Mars took centre stage. Now, with JWST and other modern telescopes, every new dataset seems to challenge an old assumption. Heat flow is not behaving the way standard models predicted. Atmospheric dynamics are richer and more variable than you were told. Ring-moon interactions are more active. The magnetosphere is more complex and more important for energy transport than the basic diagrams showed. And this shift doesn't stop at our own solar system. As soon as Uranus starts to look like a real messy evolving ice giant, with all these interconnected systems, it forces you to rethink how you're interpreting similar-sized planets around other stars. Those sub-Neptune and mini-Neptune exoplanets you see in catalogues stop being vague blobs and start looking like cousins of a world you finally understand better. The stakes climb fast because every mistake you made about Uranus has probably been copied into your assumptions about them. So the obvious question now is, if Uranus is being upgraded from a punchline to a key reference world, what does that do to your view of the wider galaxy? When you realise that most of the exoplanets we've found sit closer to Uranus in size and structure than to Jupiter, suddenly this misunderstood ice giant isn't just about correcting one old story, it's about rewriting how you read entire planetary systems. How do you build a picture of the galaxy when most of the planets you've found look more like Uranus than anything you grew up seeing in posters? When astronomers started finding exoplanets in large numbers, the big surprise was the crowd in the middle, worlds between Earth and Neptune in size and mass. Sub-Neptunes, mini-Neptunes, whatever name you use, a huge fraction of confirmed exoplanets sit in that range. They are not huge like Jupiter, they are not small like Earth, they are Uranus-ish, but for years a lot of early models treated them like scaled-down gas giants. Just shrink Jupiter's structure and turn the temperature knob. That shortcut was convenient and wrong. Structurally, these planets are closer to Uranus and Neptune, with large fractions of heavy elements, deep volatile mantles, and maybe only relatively thin hydrogen-helium envelopes. If your template for this class is small Jupiter, you start off with the wrong internal layout, the wrong heat flow, and the wrong expectations for their atmospheres. You're using the wrong reference planet. Now push those Uranus-like worlds inward. Hot Neptunes and warm sub-Neptunes that sit much closer to their stars than Uranus does to the Sun, they get hammered by stellar radiation. Their upper atmospheres are heated hard, their escape rates go up, their chemistry gets stirred by ultraviolet light. But the basic physics under all that is still set by the interior structure, the same kind of structure Uranus represents. how hydrogen mixes with heavier volatiles, how steep the temperature gradient is, where condensates like water and methane can form, all depend on whether the planet is an ice giant type or a gas giant type. When you look at an exoplanet spectrum, you're seeing tiny dips in starlight as the planet crosses the star, wavelength by wavelength. You use models to translate those dips into compositions, temperatures, and cloud properties. If your Uranus in those models has the wrong ratio of hydrogen to ices, or the wrong heat transport, you misinterpret the data. You might think a planet has a very high metallicity, when really your template atmospheric scale height is wrong. You might misjudge how thick the clouds are or where they sit. Every bias in your Uranus picture quietly bleeds into how you read those spectra, then layer magnetism on top of that. Exoplanet magnetospheres influence radio emissions, auroral signals, and how fast atmospheres are stripped by stellar winds. You want to know if a close-in Neptune-sized world is holding onto its gas envelope or being peeled like an onion. That depends on the shape and strength of its magnetic field. If all your mental examples are Earth-style, roughly centered, not too tilted, you're missing a whole range of real possibilities. Uranus throws a different geometry at you. Its magnetic dipole is offset from the center, tilted by almost 60 degrees from the spin axis, and spinning in a sideways orientation relative to the Sun. That creates a magnetosphere that is constantly reorienting with respect to the solar wind, with regions of strong and weak shielding moving around as the planet rotates. That kind of crazy architecture is exactly what you should expect on many exoplanets with thin dynamo shells or layered interiors, especially in the ice giant mass range. It's not exotic. It's happening in your own solar system. If you can't explain how that field is generated, how it evolves over a Uranus year, and how it couples to the atmosphere and rings, you're not ready to interpret a weird radio signal or an auroral hint from a distant hot Neptune. You'll be tempted to force Earth-like or Jupiter-like models onto data that doesn't fit them, when the right comparison was Uranus all along. Now look at the rest of the Uranian system as a mini-lab for exomoons and exorings. The faint dark rings around Uranus, sculpted by tiny moonlets like that 10-kilometer S/2025U1, show you how narrow rings can survive, how dust spreads, and how small bodies can find debris. The big moons, Miranda, Ariel, Umbriel, Titania, Oberon, give you examples of icy satellites that may host subsurface oceans, respond strongly to tides, and get resurfaced in patches, not all at once. When you talk about exomoons, you're usually working off subtle changes in transit-like curves, tiny extra dips or timing shifts as moons and rings move in front of their stars. To decode those signals, you need realistic templates for what a ring-moon system around an ice giant actually looks like. How wide are the rings likely to be? How bright or dark? How many small moons sculpt them? How often do you expect impact debris to cloud the system? Uranus is a nearby version of that, with faint rings, moonlets, and larger moons all in a complex dance inside a tilted magnetosphere. If you ignore that and rely only on Saturn as your mental picture of rings, you bias yourself toward bright, icy, broad structures, which might not be the norm in other systems. You might miss dimmer, narrower rings or misinterpret odd transit features because you haven't internalized how a Uranus-style system behaves. In a real sense, the Uranian system is your Rosetta Stone for translating future exomoon and exoring detections into actual physical layouts. This is where the big jump happens. Uranus isn't a weird corner case you can safely ignore. It's representative of one of the most common planetary types we know about. Every time you analyze the spectrum of a Neptune-sized exoplanet, every time you model atmospheric escape for a sub-Neptune, every time you speculate about exomoons around ice giants, you're using assumptions that trace back, directly or indirectly, to what you think an ice giant is. Whether you admit it or not, there is a piece of Uranus in those models. If that piece is wrong, or if you still think gas giant light, if you ignore the sideways tilt, the missing heat, the crooked magnet, the hidden storms, the rings, and the possible ocean moons, then your view of the galaxy is skewed. You're misreading how common certain atmospheres are, how long planets hold onto their gas, where magnetic fields help or fail to protect, and where liquid water might exist far from any traditional habitable zone. So the stakes are no longer about fixing one planet's reputation. They're about whether your framework for reading entire planetary systems is accurate. And once you connect all those threads, the tilt, the missing heat, the magnetosphere, the rings, the moons, the exoplanet analogues, one more question lands with full weight. What event in Uranus's early life could have set up so many of these odd properties at once? And what does that say about how violent planet formation really is? Not just here, but everywhere. How many of Uranus's weird features do you really need before you stop calling them coincidences and start suspecting something violent in its past? Line them up. You've got a spin axis tipped by about 98 degrees, a planet essentially rolling around the sun. You've got a strangely low internal heat output for its size. You've got a magnetic field that's tilted hard, offset from the centre, and probably generated in a thin shell instead of a deep core. You've got hints of a stratified interior, layers that don't mix heat well. When you put all of that together, one explanation keeps popping up in the models: a giant impact early in the solar system's history. Simulations where a body a few times Earth's mass smashes into a forming ice giant like Uranus can do several things at once. They can knock the spin axis way over, to something close to that 98-degree tilt. They can strip or rearrange outer layers, changing how much hydrogen and helium the planet ends up with. They can stir the internal structure or, under some conditions, separate it into distinct layers that don't mix easily. In other words, one huge collision can explain the tilt, the weird thermal behaviour, and the odd magnetic setup in a single event, instead of needing separate explanations for each anomaly. To get a feel for what that collision means, forget the word impact as you normally use it. This is not a rock hitting another rock. You're talking about an object Earth-sized or larger, moving at orbital speeds of tens of kilometers per second, slamming into a young Uranus. The kinetic energy involved is on the order of 10 to the 29th joules or more. That's many orders of magnitude beyond anything you ever deal with on human scales, far beyond all nuclear weapons ever built, far beyond the total annual energy use of human civilization, multiplied by absurd factors. At that scale, rock and ice don't behave the way you're used to. They melt, vaporize, and flow. Huge fraction of the impactor and some of the outer layers of Uranus would be blasted into a hot, extended cloud. Some of that material would fall back, some would be flung into orbit. Inside the planet, shock waves would race through, mixing some regions, separating others by density, and possibly leaving behind an interior where heavy and light components settle into complex layers. You're basically rearranging the entire planet, not just denting its surface. Now look around Uranus today and ask, where are the traces of that event? One candidate is right in front of you, the rings and the inner small moons. Those narrow, dark rings and the compact inner satellites could be descendants of debris thrown into orbit by that ancient collision. Their orbits, their spacing and their total mass might encode how much material was lofted, how fast it was moving, and how it reaccumulated. The fact that the rings are dark and made of likely carbon-rich material might point to the composition of the disrupted outer layers or of the impactor itself. The small inner moons, especially the tiny ones acting as ring shepherds, are also part of that story. They may have formed directly from that debris disk, sweeping up fragments until they reach their current sizes. Looking at their sizes and positions is like looking at fragments of shrapnel and where they landed. You're not just cataloguing rocks, you're trying to read the pattern to reconstruct how the original explosion happened, what angle it came from, and how much energy was released. The same event that knocked Uranus over and created debris could also have locked in its magnetic oddities. If the collision changed where the electrically conducting layers sit, for example, confining a conductive ocean of superionic ices into a shell at certain depths while leaving other regions less mixed, you'd naturally end up with a dynamo that doesn't look like Earth's. Instead of a roughly centered, mildly tilted field, you get one that's strongly tilted, offset, and possibly concentrated in particular latitude bands or depths. Fast forward billions of years, and that internal arrangement is still controlling where and how currents flow. The result is the tilted, offset magnetic field you measure today, the one that produces shifting auroras and a magnetosphere that looks nothing like the neat textbook diagrams. So when JWST maps auroras and measures upper atmospheric temperatures, you're seeing the present-day effect of a field that was probably shaped by a single catastrophic event long before life existed on Earth. This origin story isn't just about Uranus's personal trauma. It matters for how you think planet formation works everywhere. Giant impacts are not a fringe idea in planetary science. They're invoked to explain the Moon's formation around Earth, the odd spin of Venus, strip mantles on some asteroids, and more. For super-Earths and mini-Neptunes around other stars, large collisions are expected during the chaotic early stages, when protoplanets cross orbits and slam into each other. If Uranus is an ice giant that actually kept a clear record of one of these impacts in its tilt, interior, rings, moons, and magnetic field, then it becomes your best close-up lab for testing what giant collisions really do. Does one impact usually just tilt the axis? Or can it also suppress internal heat loss for billions of years? Does it always leave behind a debris disk that turns into rings and moons? Or does that depend on angle and speed? Does it tend to produce offset shell-based dynamos? Or is Uranus unusual even among impacted planets? If you misunderstand Uranus's past, you misread those answers. You might underestimate how often impacts reshape interiors instead of just surfaces. You might misjudge how many exoplanets had their atmospheres stripped or their spins scrambled by collisions. You might miss the link between a weird magnetic geometry and a violent history. In other words, you'd be walking past scars of planetary violence, both here and in other systems, and calling them odd quirks instead of what they are, evidence. And that leads straight into the final turn of this whole story. If Uranus really is the product of a massive ancient collision, if its tilt, rings, moons, magnetosphere, and maybe even its missing heat all trace back to that one event, then leaving it understudied is not just a gap, it's a huge wasted opportunity. The next big step is obvious. You stop guessing from one flyby and a handful of telescope images, and you send a dedicated mission to park there, map everything, and watch it evolve. The only question is whether you treat that as optional or as one of the most important unfinished jobs in exploring the outer solar system. How seriously should you take a planet when the entire planetary science community basically stands up and says, "This is the next big one"? That's what happened when the 2023 to 2032 Planetary Science Decadal Survey put a Uranus orbiter and probe at the top of the flagship wish list for the outer solar system. That report is where scientists fight it out, argue priorities, and then tell space agencies, if you can only afford a few huge missions, send them here. Putting Uranus at the top is not a polite suggestion, it's a correction. A clear signal that we've let a key world sit in the dark for decades, and that delay is now a problem for the whole field. So what would an actual orbiter do that changes everything beyond better pictures? First, it would map the gravity field with high precision. By tracking how the spacecraft speeds up and slows down as it flies over different regions, you can infer how mass is distributed inside the planet. That finally pins down whether Uranus's interior is strongly layered, how big the core is, and how the ices and rock are arranged. No more hand-waving about maybe it's like this. You get real constraints. Then you drop a probe into the atmosphere. That probe would fall through the upper layers, sending back direct measurements of temperature, pressure, winds, and composition as it descends. You would get actual vertical profiles instead of guessing from spectra. How much water, how much methane, how much ammonia, how the temperature changes with altitude, all of that would go from model-dependent to measured. That is the difference between guessing and knowing. The orbiter wouldn't stop at the planet, it would dive past the moons over and over. Close flybys of Miranda, Ariel, and the others at only a few hundred kilometers up, a few hundred miles, would let you map their surfaces in sharp detail, measure their gravity fields, and track tiny wobbles in their rotation, their librations. Those wobbles tell you if the interior is solid all the way through, or if there is a decoupled liquid layer, a subsurface ocean, letting the outer shell move slightly differently from the core. Instead of one set of grainy Voyager snapshots, you could watch the whole system evolve over years, across seasons, under a changing sun angle. That leads straight into the big habitability question. Are there real oceans hiding out here, and how long have they lasted? With an orbiter, you can combine gravity and shape measurements, thermal data and magnetic signatures to look for conductive, salty layers under the ice, the same way we do at Europa or Enceladus. You can fly low over trenches on Ariel, scan coronae on Miranda, and see whether those features line up with internal structures. If even one Uranian moon turns out to host a long-lived, energy-rich ocean, you just blew up the old, tight view of the habitable zone. Suddenly, the outer solar system has more real estate, more environments where liquid water and chemistry could run for billions of years, tucked under ice, far from the sun. And if more than one moon qualifies, you're looking at a whole cluster of potential ocean worlds around a planet that used to be a meme. At the same time, every in situ measurement you make at Uranus feeds directly into exoplanet models. Right now, when you see a sub-Neptune in someone's paper, you're making assumptions about how its atmosphere is structured, how much heat it leaks, how its magnetic field interacts with the stellar wind, and how any rings or moons might behave. All of those assumptions are informed, whether you realize it or not, by Uranus and Neptune, a Uranus orbiter that measures the atmosphere's vertical structure, the real heat flow, the exact magnetic field geometry in different seasons, and the detailed layout of the rings gives you hard input for those models. You can calibrate them against a real ice giant, not just plug in numbers that kind of work. That sharpens your interpretation of spectra from JWST and future telescopes, letting you say with more confidence, this planet probably has a thick volatile mantle, or this one is losing atmosphere fast, or this one might have enough magnetic shielding and tidal action to support active moons. And that's the twist. The mission doesn't just fix your view of one neglected planet, it upgrades your toolkit for reading thousands of worlds you will never visit. The payoff is not just a better Uranus poster, it's better physics across the board. So here's the final punch. For most of your life, Uranus has been the joke planet, the one everyone snickers at and then skips. But when a Uranus orbiter and probe finally fly, that hierarchy flips. Suddenly, this background world becomes the keystone that ties together giant impacts, crooked magnetic fields, missing heat, hidden oceans, ring moon dynamics, and exoplanet analogues. The planet you were trained to laugh at turns out to be the one holding critical answers about how planetary systems really assemble, break, and settle down. You haven't just been underrating Uranus, you've been sleeping on the main character in a story about ice giants, exoplanets, and violent origins. Once the data start coming in from a dedicated mission, you won't be able to keep calling it a side note. You'll have to admit what the science has been hinting at for years. The punchline planet was never the joke, it was the missing piece. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.